Okay, so today I'm going to be talking about section 9.3 from our book, which is the over the argument principle and Rouche's theorem. But before we dive into those, I think it's important to set up a bit about section 9.2, which leads directly into the argument principle. And 9.2 talks about the residue theorem, which states that the integral on gamma of a function f is equal to 2 pi I times the residue at z equals, we'll call it zi for now, phi of z. And what some of the conditions are, we can have, we would call this our area gamma, and then it's in some plane G, which we can mark there, which we mark as there, so that's our G. Then we can let these dots be singularities. And then some conditions we need is for f to be holomorphic, so it can be derived at every point in this curve gamma, apart from these singularity points. Then some conditions imposed on gamma is it has to be positively oriented, which means you can go around it in the counterclockwise direction. Then it has to be so it has that positive orientation, then it's simple, closed, and then piecewise smooth, and none of these singularities are on the boundary. So we can call this Z1 right here, this probably Z2, then we have Z3 and Z4. And basically what we can do is we can draw these little curves around each one, and we can calculate the residues of all those points right here with a function that's holomorphic everywhere around those points except for those points, and then we can get the integral of the entire area from that. But however, how this leads to the argument principle is that we may not always have a function f where we can find the singularities. So in other words, we don't always know where the singularities are at, so we won't always be able to do this step straight away. And that's where the argument principle will come in. And so since we don't know where the singularities are, our next step would be to try to find where the singularities are, which will lead us to the argument principle. But before that, there is something that we should probably introduce, and that's called a logarithmic derivative. So the first thing we're going to do for that is we're going to let f be a differentiable function, which essentially just means that it has a derivative that exists. And then what we can then do is we can do the log of f, where log is just a branch of the logarithm, because a logarithm can have multiple branches. So that is just one branch of the logarithm. And then we can take the derivative of that, and the logarithmic derivative becomes f prime over f. And then this is what we would call the logarithmic derivative. And then this does have a rather nice property, where if we were to let f and g be holomorphic on a region capital G, then we can write their logarithmic derivative as f g prime over f of g. And then when we evaluate this derivative, it is just going to be a product rule. So we have derivative of the first, which is f, g, times the second, which is bg. Then we have plus the first, which is going to be f, times the derivative of the second, which is going to be g prime. And then that's still over fg. Then we can go ahead and separate the terms out. So we have f prime of g over f of g, plus f of g prime over f of g. And as we notice, we can go ahead and cancel g on this part and f on this part. So we have the logarithmic derivative of fg prime over fg is going to be equal to f prime over f plus g prime over g, which is going to be very useful for us when we end up proving the argument principle. Before we do that, we do still have a couple more things that we need to go over first. Okay, so since we now have that this is equivalent to this, we can now apply this fact to a following situation. So where we're going to let f be holomorphic in a region G, and we're going to say that f has a finite number of zeros in G. And we can go ahead and label those zeros as Z1, Z2, all the way up to, we will go ahead and call it Zj. And then every zero in F also has a multiplicity. So there are going to be these zeros here of multiplicity. And we can go ahead and label the multiplicities. We're going to use n for the multiplicities. So there'll be a multiplicity n1, n2, all the way up to nj, where n1 is the multiplicity of z1, n2 for z2, and nj for zj. And then we can use theorem 8.14 to write that we can write f as a function of the zeros and their multiplicities. So think of it like writing x squared minus 2 times x plus 1, where all those are all the zeros of the functions that become the actual function. So that's more of a specific form. But for the generalized form of this, we would have that f of z is going to be equal to z minus z1 n1 times z minus z2 n2 multiplied by all the intervening terms all the way up to z minus zi, or no, we're going with j, not I, so cj, nj. And of course, and there's one part we can't forget, we're going to have a g of z as well. And an important fact about g is that little g is also holomorphic on g, but most importantly, g is never 0. And that will be very important for later when we prove the actual argument principle. But then if we were to then go ahead and do the logarithmic derivative of this again, so it'll be very similar to this, where we're going to do a one long product rule on the top, and then we're going to cancel some terms out. So I'm just going to only do the first term and then 2 of the last terms, just to save a little bit of space and a little bit of time. So we're going to have n1 z minus z1 to the n1 minus 1, and that's going to be time multiplied by all the other terms up to that. And we would do, then the next one would be z minus z1 times n1, then the derivative of the second term. So we're going to skip all of that to all those extra terms and just go to the n. So we'll have, not n, so we'll have a z minus z1 n1, and then it's going to be times all the terms. Then we're going to have z minus zj nj. Then we're going to have the derivative of g of z. So we're going to have that derivative at the end as well. Then we're going to have just the original term again at the bottom as a denominator. So we'll have z minus z1 n1, z minus z2 n2, all the way to z minus zj nj times g of z. And that's what we will have for the logarithmic derivative. And then we can go ahead and cancel out like we did over here, and we see that we end up with n1 over z minus z1 plus n2 over z minus z2 all the way up to nj over z minus zj plus g prime of z over g of z. And then that is what we have as the logarithmic derivative for f, which is just going to be, essentially it is the multiplicity of the zeros divided by the location of the zeros plus this holomorphic g prime of z over g of z at the end. Okay, so now that we've shown we can write the logarithmic derivative of all the zeros like this, you may be asking, what about any poles that are in f as well? And we actually have an equation for that one too. So we can, same conditions where f is holomorphic in G, we can say that f also has a finite number of poles in G. And we can define those poles as P1, P2, and we'll go ahead and say all the way up to, call it PK. Then each pole, similar to how zeros have multiplicity, poles have orders. So they will be, each pole will be of order, and we will go ahead and call them M. So we'll have M1, M2, all the way up to MK. Or M1 is the order of P1, M2 order of P2, and MK order of PK. And then we can also write this as an equation like this one, including the GZ, but just to save a little bit of time, I'm just going to go ahead and skip down to what its logarithmic derivative will be as well. So for that, we will see that f prime of z over f of z is going to be equal to negative m1 over z minus p1 minus m2 over z minus p2, and keep subtracting all the way to mk plus z minus pk plus g prime of z over g of z as well. So we now have an equation for f prime of z when it's the zeros, and f prime of z when it is the poles that are in here. And as you can see, it's very similar to the zeros. The poles is going to be the order of the poles over the location of the pole. And essentially, another thing that we've done that will be very important in a moment is we have essentially turned this is essentially now a pole of order 1, a simple pole of order 1 at z equals z1. And this is a simple pole at z equals z2. This is a simple pole at z equals p1, and a simple pole at z equals p2. Which is very important for the next part that we need right before we do the argument principle, is the definition of a meromorphic function. So, just a quick one. F is meromorphic if f is holomorphic on G apart from its poles. Which is why it's important to note that these are all now simple poles of order 1. Because that lets this be true for our function f now. Okay, so now that we've managed to lay all of that groundwork, we can now jump into Theorem 9.17, which is the argument principle, which I already wrote on the board, so I figured it'd be easier to read it out to you than try to talk to you and write it. So we're just going to suppose that f is meromorphic in a region G, then gamma is positively oriented, simple, closed, piecewise smooth path, but does not pass through any of the poles or zeros of f, which is very similar to, almost identical to what we had for the residue theorem for gamma. We also have that gamma is related to 0 like that, so that basically means that the gamma can be continuously contracted until it is essentially 0. And when we have these conditions met, we can denote by this term right here, z of f gamma. This will be the number of zeros of f that are inside their path gamma, and they're going to be counted by their multiplicity. They would have p of f of gamma. That'll be the number of poles of f that are inside gamma, and they're going to be counted by their order. And with that, we then get this nice little equation right here, that 1 over 2 pi I times the integral of the logarithmic derivative of f is equal to the number of zeros minus the number of poles. So a nice little picture real quick would be that, so here will be our gamma, call that gamma, and it's positively oriented, and all the other conditions are met, and then we're going to let the green dots, these are going to be our zeros, and then the red dots, we're going to let them be our poles. So you can see gamma does not pass through any of the poles. So if we add up the zeros real quick, so we have that, so from this we'll have that 1 over 2 pi I integral of the logarithmic derivative is approximately going to be equal to, we have 5 zeros, and then we also have, it looks like 6 poles, so we'll have 5 minus 6, which is going to be negative 1. Oh, negative 1. Oh. Negative 1. So we'll have that the integral of the logarithmic derivative divided by 2 pi I is going to be -1, which would tell us that this integral itself is going to be equal to -2 pi I, because -2 pi I divided by 2 pi I, so it gives us -1. Okay, so what the argument principle does for us is it helps us locate the poles and zeros of a function f. So if you notice, we did not integrate f, we integrated the logarithmic derivative of f. So our first step is we're going to do exactly what we did here. Integrate it over a big circle gamma, so let this be our big circle gamma. Then the next step will be to we're gonna go ahead and dissect this like that. So this now becomes gamma 1 on this side that goes that way and keeps going that way. And we're going to come back inside and we're going to have a gamma 2 now. As you notice, it is roughly half the area of this. So if we were to now integrate over gamma 1 of f prime of f, we would have z of f still, but now it'd be gamma 1. Then that'd be minus p of f of gamma 1. And then we would keep doing that, so now we can do that again, and now we have a gamma 3, which is just going to be this section here. And then we would do that again over gamma 3, and it'd be z, the zeros of f of gamma 3, minus the poles of f on gamma 3. And essentially we would keep doing that until all of the singularities are in a region by themselves, which we have here. And then we would be able to take an integral, say, we can do this one right here. So then we can integrate around this path right here. And then when we divide by 2 pi I, that'll give us the residue of that point. And we can repeat that process for every other singularity in here. And then we now have the residue. Then we can now calculate the residue at each of those points, which then from the residue theorem will give us the value of the integral of f over the entire gamma. And that's essentially what we do with the argument principle. Okay, so after going through that quick proof of the argument principle and then kind of how it works, we can go on to an application of the argument principle, which is Theorem 9.18, which is Rouche's theorem. And this says that suppose f and g are both holomorphic in the region big G, and then gamma is a positively oriented, simple, closed, piecewise smooth path, such that this is true. Then we can see that, and then another condition is that mod f of z is greater than mod g of z for all z that are an element of gamma. That essentially means for every z on the boundary of gamma. Then we have this, the zeros of f plus g in gamma is equal to the zeros of f in gamma. So what this will do is it allows us to locate the zeros of a function fairly precisely. And a quick example would be to say let the polynomial p of z equals z to the 5th plus z to the 4th plus z cubed plus z squared plus z equals 1. And for this we can go ahead and we can let gamma equal the circle centered at 0 of radius 2. And one thing that some people may not be able to see right away, not equal 0, not equal 1, plus 1, is that every root of this polynomial here has essentially a modulus of less than 2. Essentially, their multiplicity is 2 or less. And what we can do here is we know that gamma satisfies all these conditions on center at 0 radius of 2. So we need to make sure this is true. So for that, we can define our f of z. Let that be z to the 5th, in which case g of z is going to be z to the 4th, plus z cubed, plus z squared, plus z plus 1. And then, so at z equals 2, mod f of z is just going to be evaluating it at 2, because every point, every z on this gamma is going to be 2, because the radius is 2. So no matter what, wherever you are on gamma, z is going to be 2. We're going to plug in z for 2. So we're going to have 2 to the 5th which is going to be 32. Then mod g of z, we're going to do the same thing. So we're going to have 2 to the 4th, plus 2 cubed, plus 2 squared, plus 2, plus 1. So we have 16 plus 8 plus 4 plus 2 plus 1, which is going to be 31. So we have 32 is greater than 31. So f of z, ooh, let me write that a little less crooked. So we have 32 greater than 31, implying that mod f of z is in fact greater than mod g of z. So now that we have that, all the conditions are met. So we know that the zeros of f plus g of gamma are going to be equal to the number of zeros on f plus gamma. And we have f of z is equal to z to the 5th. So there's only one place where z to the 5th is 0 on the circle 0, 2. And that's going to be at equals 0 at z equals 0. And then you can also notice that it's not just that they're one time, it is in fact there 5 times. So it's 0 of multiplicity 5, which implies that z of f on gamma equals 5. So there's 5 zeros on f, which from this formula, from the theorem, from Rouche's theorem, tells us that the number of zeros on f plus g of f plus g on gamma is equal to 5 as well. And if you were to plug this equation, this function into this polynomial into a roots calculator, you would also see it would in fact tell you that there are 5 zeros inside of there.